We will wait for a couple of minutes for others to join. After that, we will start. Okay, let's get started. May I audible to you?
Yes, sir.
Okay, okay, Babu. So this is the live session 2 on the course of manufacturing process technology first and second. So in in this session we will solve some of the practice assignment questions based on the video lectures of the second and third week of the course. So quickly let's get started. So this is the problem one. Please read the problem and first try to solve it by yourself, and after that we will discuss it together. So please read it and you can give your answer in the chat box. Okay, okay, Vaibhav, you have given answer D. Okay, let's try to discuss it together. So uh, let's discuss it one by one. Okay, so in this question, it has been asked which of the following phenomena is not correct. Please note down the word not correct with respect to the mechanism of the wear. So first one is the abrasion. So let's try to understand the abrasion quickly. So abrasion is a type of wear, and we know what is wear. Wear is a uh, gradual loss of material, gradual loss of material. Basically, when two bodies are in the contact, and then because of the contact, some over the period of time, and one of the material, one of the bodies, it loses its material, and that is called the wear, and this is undesirable phenomena. So so there are different mechanism of the wear. Out of them, one is the abrasion wear. In abrasion wear, what happens? Suppose we have two bodies, let's say it is like here, and suppose we have another body, Okay, and suppose one of them is harder, this one is harder, and this is softer. Now what I will do, I will when these two body comes into the contact, so this is the surface of the body. So if you microscopically, if you see by the microscope, any surface is not very flat. So there are spurties. So these kind of spurties will be there. And when we keep two bodies, suppose if we are saying that these two bodies are in the contact, it doesn't means the complete surface area of these two bodies are in the contact. So only few portions, basically the portions which are coming out of the surface, like small spurties are there, so they are coming in the contact, whereas the other portions are not coming into the contact. So if two bodies are there, one is harder, one is the softer, uh, so what will happen when they are in the contact and there is relative motion between them, then what will happen? The harder body, it will try to remove some material from the softer body. So this type of wear is called the abrasion wear. It is a example of two body abrasion. Similarly, there is a possibility of three body abrasion. Suppose we have two body like this, and in between we have some hard particles. So this is the harder particle. Then also when there is a relative motion between these two bodies and in between there is a harder particle, then what will happen? This harder particle will remove material from the both upper body and lower body. So this is also example of abrasion wear. It is called three body abrasion, and this is the two body abrasion. So material removal because of the harder particle from the softer body, that is the example of abrasion wear. Now let's come to the diffusion wear. So diffusion wear, it is a slow process and it happens mostly at the elevated temperature. The most common example is if you know about the cutting process. Suppose we have a material which we are cutting from a cutting tool. Okay, so this is the tool and this is the workpiece, and this is the chip. What happens during the cutting process? If the cutting velocity is too high, if cutting velocity is too high, then near this region, in this region, the temperature increases, and because of increasing temperature, if there is a possibility of diffusion, when diffusion happens because of concentration gradient. Diffusion, it happens because of concentration gradient. For example, suppose we have a, cutting tool made up of, let's say, high speed steel um, or any steel which have high carbon. So this is made up of HSS or some steel which have high carbon, and this workpiece, it is also some material which has carbon, but suppose that it is mild steel. It has less concentration of the carbon or less amount of the carbon. When these two comes in the contact, here since suppose that we have higher concentration of carbon, here less concentration of carbon we have. When these two comes in the contact and because of the cutting process at high velocity, heat is get generated, and because of this heat, the carbon atoms, they will start moving from high concentration region to low concentration in the point of contact region. So again, material is being lost from tool to the workpiece. So what happened? Gradual loss of material is happening here, but here the process is the diffusion, and this diffusion arises uh, because of the concentration gradient of carbon atom in the tool to the workpiece. So this is the diffusion here. So if we see the what is written, the concentration gradient based movement of atoms. Yes, it is correct. And similarly, if we see the first statement, hard particles dislodge the material from the surface of contact by flying. Yes, it was also correct. Basically, a hard material was removing the material from the softer material. And let's see what happening in the third one. Addition. These similar metals in the contact break apart that surface in the contact. So let's quickly discuss about the uh, addition here. So what happens here? So it was diffusion. In addition, for example, if we have two bodies, okay, and we have applied some load between them, and same time what we are trying to move, shift, or we are trying to give some relative motion between them. So if if because of the load, and there is a localized welding takes place between them asperities. So these are the points where material got deformed plastically, as well as both material got welded at very local region, here. So micro welding has taken place between these two body, and when relative motions happens between them, then what happens? A chunk of material, a chunk of this welded region get chipped off, and it's get taken away by one of the component. So here also material is being removed, but that happens because of the localized welding. So because of the localized welding, the material got stick to one of the bodies, and that got chipped off from the other body. That's why one of them will lose the material, and this process happens slowly. And since here also the body is one body is losing the material gradually, that's why it is also a wear, and this type of wear is called adhesion wear. So in adhesion wear, the main thing is this type of localized welding has to take place, and is that has to be removed by the one of the bodies. So but if we see the for addition, this similar metal in the contact break apart the surface in contact. So it is not correct definition here. They are not. It is it has not been said anything about the localized welding, and also here these similar metals. This is not valid also. So it can happen to any type of material. So it is not correct answer. So this is the wrong one, but the question it has been asked, which is not correct. So for this question, correct answer will be the C, addition here. Okay. If you have any doubt, you can ask me. Otherwise, we will move to the next problem. Okay. Okay, then let's move to the next problem. Uh, Read the question and you can give your answer in the chat box. Yes, Pepper, you are correct. So, uh, so for everyone, I will explain the answer. It has been asked in the equilibrium phase diagram, the line here, this is the fill in the blank, and we have to fill this by correct appropriate word. The line is the line above which there is only liquid, liquid composition present in the system. So, if we see any phase diagram, suppose suppose for simplicity we are taking binary phase diagram. Let's say we have A and B. These are the two materials, and we are trying to make a phase diagram of for different composition of these two materials A and B. Here we have 100% A. Here we have 100% B, and on the y-axis we have temperature. So if we draw the phase diagram, so for example, we will get something like this. So at higher temperature, whatever composition of A and B will take, we will get liquid, and at lower temperatures, whatever composition we will take, we will get solid, and in between the solid and liquid region, we will get liquid plus solid region. And there are different names given to these two lines, this line and this line. So this line is called the liquidus line, and this line is called the solidus line. So correct answer is the liquidus line, because the line above which there is only liquid, so that line is this one. So above it only liquid is there, so correct answer is B. So let's move to the next problem. Please read the question and try to answer it by yourself. After that I will discuss it. Please read the question and you can give your answer in the chat box. After that we will discuss it together. If you are having any difficulty to understand the problem, please you can discuss with me. Okay. Okay, I have got response from the web hub. So let's quickly discuss it together. So in this problem, what has been which of the following is not true for the eutectic point in the equilibrium phase diagram? So let's try to see uh, where is the eutectic point. So if we take eutectic system, so uh, it is also a system of two materials, A and B, but here here it is little different from earlier which I have drawn. So this kind of system where we get uh, two phases after solidification, and in between, if we see for different composition, we get different ratios of those phases. So this kind of system is called the eutectic system, and this is a very special point. It is called a eutectic point. So there are it has many features. So let's start looking each option whether they are correct or not for this point. So first one is it's the specific composition of two metals which has a specific or not a range freezing point. So what is here? So all this reason, if we see all this reason, this is liquid region, and this is phase alpha, and this is phase beta, and this is liquidus. Here also it is liquidus. Okay, and here liquid plus beta. So basically two types of phases forms at different compositions. So let's see for this region. Suppose we have material which we have heated it, we have given it sufficient heat so that it comes into the liquid region, and now suppose that composition is somewhere this. Okay, here we have, let's say, 20% A, so 20% B, and 80% A, for example. So if we take this composition and we heat it sufficiently so that all the material gets melted down, so we will be here. And now what we do, we'll try to decrease its temperature and we will see what is happening. So if we start decreasing its temperature, so at this point what will happen, the liquid phase now starts to become solidified, means some of the material will start gets solidify, and liquid and solid phase both will remain together. But after this line, so this is the solidus line. So in this region, if we see what will happen, the all the liquid phase will go away, only we will have solid phase. And if we cross this line, then we will get some amount of alpha and some amount of beta. So here this was the point of starting of solidification. Similarly, this is the point where solidification process got completed. Completion of solidification. So we got a range. So here the temperature was something this, and here it was some. So we got this much range of temperature for the during the solidification. But if we see eutectic composition, this special composition is called eutectic composition, and the biggest feature of this point is that here the whole material will get solidified directly from liquid to solid. We don't get liquid plus solid region. So directly from liquid, if we starts reducing the temperature, suppose we have starting, we are here, and then we start cooling down the material. Then after eutectic point, so this temperature, this is called eutectic temperature or TE. So after this temperature, what will happen? The whole liquid directly convert into alpha plus beta. We will not get any region of liquid plus some solid region. Earlier, like here, we were getting liquid plus alpha region. So that is the one one feature of this eutectic point. Another feature is uh, this is the point, or we can say this is the mm, minimum. This is the minimum temperature at this composition. It is the minimum temperature where we can get the liquid. Suppose here what will happen? Suppose we took the eutectic composition and we try to heat it. So when we try to heat it, its temperature will increase, and as soon as we will reach the eutectic temperature, after that complete material will gets converted into the liquid. Whereas if we take any other composition, then in order to make it complete liquid, we have to add more heat, or we have to increase the temperature little higher. So suppose that, for example, here we are taking some composition. So after this point, we will get only few part of liquid, and if we heat it more, if we increase the temperature little more, then only we will get complete liquid. So this is the special composition. Now let's try to read the second option. It's the point temperature where liquid instantly converts into the two solid phases. Yes, correct. So indirectly it is saying we are not getting liquid plus solid region. So this is correct. And first one was, it was also correct, because here we are not getting any range of the solidification. Now let's read the third point. It's also called an easy melting point. Yes, this is the point which I have discussed just now, that the material at this composition, the material will melt very at low temperature. That means its melting point will comes down. So it is also correct. So since all of these are correct, so correct answer will be the D. All of above are correct. So is it clear? If you have any doubt, please ask me. Or okay, it's clear. Then we will move to the next problem. Okay, please read the question and try to give your answer in the chat box. Yes, correct, Vaibhav. So let's quickly see solution of this answer, solution of this problem. So it has been asked, how much iron does cementite contain? Cementite means what? Fe3C. So uh, if you know, then let's try to calculate its its weight of this composition. Okay, so here we have 3 atoms of iron and 1 atom of carbon, and weight of iron is, it is 55.84 gram per mole, and similarly weight of carbon is, it's 12.01 gram per mole. And now what has been asked, how much iron. So if we try to calculate weight percentage of iron in Fe3C, what we have to do, we have to take the weight of the iron divided by weight of Fe3C into 100. So that will be equals to 3 times multiplied by 55.84 divided by the complete weight, which will be equals to plus 1, since we have only one atom of carbon, so its weight will be this much, and we will multiply it by 100. If you will solve it, then you will get, roughly means, you will get approximately 93.3%. Okay, so yes, it was easier one. So let's move to the next problem. Please read the problem and you can give your answer in the chat box. Okay, I have got response from the webho. Okay, let's start looking one by one. So here it has been asked which of the following is incorrect combination of alloying element and its effect on steel. So first one is the phosphorus. So yes, it, it is the one of the alloying element. So what properties we get when we add phosphorus? So I will list it down. For P, our phosphorus, these are the property. uh, it it increases the hardenability of the steel. Hardenability, it increases. It also increases the machinability, as well as it also increases the corrosion resistance. And uh, it increases the strength. It increases the strength of, if we have low carbon steel, then in that case it increases the strength also for low carbon steels. So yes, first one is it increases the hardenability. Yes, it is correct. So it is here first. And next one is the nickel. So yes, nickel is also one of the alloying component of the steel. So what are the properties changes when we add nickel? So first one is that toughness increases, or we can say impact strength. If toughness will increase, then its impact strength will also increase. Okay, and it also increases the corrosion resistance. Yes. So both things it increases. So yes, this one, second one, it is correct. Now let's talk about the molybdenum. So if we add molybdenum to the steel as alloying element, then it increases the strength. It increases the strength as well as toughness also, hardness. So this thing will happen means when molybdenum will added along with chromium and manganese, chromium, manganese, and vanadium. So when molybdenum added in the presence of chromium, manganese, and vanadium, then all these properties gets improved, as well as it also increases the corrosion resistance, and it's since hardness is improving, then its wear resistance or abrasion resistance also increases. So molybdenum enhances the corrosion resistance. Okay, I think this there is some issue, so it should not be corrosion. So yes, it increases the corrosion resistance. It is correct, but I think this is, I think, misprint. But for corrosion resistance, it is correct. It increases the corrosion resistance. Now let's try to see manganese. Manganese also increases the hardenability, but what it does, it it decreases the ductility, as well as it also decreases the weldability. Mostly whenever either hardness or strength of any component of any material increases, same time we will losing the ductility. So but here it has been given manganese, addition of manganese will increase the ductility of the steel. So it is not correct option, since we have to find the incorrect combination. So this is the right answer for this question. Okay, so any doubt? Okay, since there is no doubt, so we will move to the next problem. Yes, please read the problem number 6, and you can keep your answer in the chat box. Yes, Vaibhav, uh, you have given the correct answer. So let's discuss it together. Which of the following form of Fe3C composition is the hardest? So austenite, martensite, pearlite, benite. So let's try to see quickly from the uh, triple T diagram, uh, temperature time transformation curve. So uh, what happens uh, if you have, if you remember your iron carbon diagram, then uh, then how it looks like something like, I am drawing just part of it. So here in this direction we increase the percentage of carbon. So if you remember, this is the temperature, and alpha this is the alpha ferrite. On above this, what we get? So if we keep on increasing the temperature of alpha ferrite, then after certain temperature, say here, if we take any composition, let's say here, if we try to heat it, then in this region, this alpha ferrite will transforms into the gamma, which is called austenite. So here the crystal structure was FCC. Sorry, it was BCC. Here it was BCC crystal structure. So if we heat it, then alpha get transformed into the gamma austenite, and here crystal structure gets changed to FCC. So usually, if we want to change the property of the given steel, then we go for the heat treatment. So what we do, we suppose we have any composition here, and if we want to change its properties, suppose it has some strength and some ductility, but if you want to change it, then what we have to do, we increase its temperature above this line. So this is the gamma plus alpha region, and in this region we have alpha plus Fe3C. So for this composition of steel, if we want to change its properties, then we will heat it, and we will homogenize is it to the gamma phase, or we will heat. Then what will happen? Alpha plus Fe3C at this composition will get converted into the gamma austenite phase. So that is shown here. So here note down its temperature is in Fahrenheit, or equivalent temperature if we write, it will come to 727 degrees Celsius. So we will heat the steel to some temperature above this 727 degrees Celsius. Let's say here. Now the properties of steel is governed by how fast or how slower we are cooling. So if we slow down, if we cool it inside the furnace, or we keep slow rate of cooling, then what will happen? We will get perlite. So this curve, it is showing the transformation curve. So this is the beginning of transformation, or starting of perlite transformation. And this curve, the inner one, this is for completion of perlite transformation. So what we first homogenize the given composition to austenite phase, and then we cooled it down slowly, and here we got the perlite. So if this cooling rate is too slow, if cooling rate is too slow, then in this region what we will get coarse perlite. And if increase the cooling rate little higher, in this range, after transformation, what we will get? Fine perlite. Coarse perlite has good ductility, but it has low strength. Fine perlite has high strength, means little high strength as compared to coarse perlite, but its ductility will be little smaller than the coarse perlite. But suppose if we further increase the cooling rate here, or if we do it of cooling rate, what will happen? We will come in this region. This is the region is called bainite. So, or we can do another thing. We can cool faster. Then we hold that temperature. Then also we will reach to the bainite range. So, if we reach here, if our transformation completes below this nose, this is called the nose. Below this nose, then what we'll get? We get bainite. So bainite has much improved properties. So it has good strength. It has very good strength, I should say, but its ductility is not very poor. So it has ductility. It has ductility which is little lesser than the fine perlite. So it is kind of good thing. Means here we got good strength as well as some considerable amount of ductility. So that is good. But what will happen if we increase, if we cool the, if we, if our cooling rate is too high, like here or somewhat here. So if the cooling rate is too high, this is called quenching process. So what will happen if we bypass this nose and directly we will hit here? This is called, this is the martensite formation line. So here we got perlite, here we got bainite. Now if we further increase the cooling rate, then what we will get? That is martensite. So this is the martensite start line. This is the martensite finish line. So if cooling rate is too high, then we will land into the martensitic region. So martensite is very hard. For the steel, martensitic phase is very hard, but it has very poor ductility. So very hard and poor ductility. So we will go for the martensitic transformation only if we are looking for the hardness, not the ductility. So this is the correct answer. That is the hardest. That is the hardest form of the any steel, and that we will get by very rapid cooling rate uh, of the austenite. So it's basically it is a diffusion less transformation, because here the cooling rate was too high. The carbon atoms, they didn't got sufficient time to diffuse in order to form some ferrite or alpha phase. Sorry, yes, ferrite phase and cementite phase. So they got very less time, and its crystal structure is BCT, body centered tetrahedral. So that is kind of distorted version of BCC, but it is very hard. So correct answer is the martensite. Okay, it is clear, or we shall move to the next problem. If you have any doubt, please stop me. Okay, it seems there is no doubt, so we will move to the next problem. Please read the problem and you can give your answer in the chat box. Okay, I have got response from Vaibhav. I'm waiting for others. Okay, let's discuss it together. So we have read the casting process. So it is related to the casting process. So it has been asked in which of the following type of gating mold is filled from bottom to top. So there we have studied two type of gating. So suppose we have this cavity, and and if you are filling this whole cavity, here we have molten metal, and if you are filling the molten metal to the cavity from top, so what will happen? The molten metal will enter inside the this is the cavity and this is the mold, and it is made up of sand. Mold is made up of sand, and we are filling this cavity with the molten metal from the top. So here this is the gate through which metal will enter inside the cavity. So this kind of gating system, it is called vertical gating. This kind of arrangement of filling the mold from the top side, this is called the vertical gating. But there are some disadvantage of this kind of filling, like if we are filling from top, then molten metal will directly fall from here to the bottom of the mold. So it is falling from this much of distance. So there is possibility, if mold strength is not very high, then it may erode in this region. So if this height is high and metal velocity is also higher, then there is a possibility of erosion in this region. So this is the one of the disadvantages of vertical gating, whereas it has advantage like metal directly, it takes less time to fill the cavity because metal is entering in the cavity directly. There is another configuration. So suppose we have cavity like this, so again this is our cavity, this is cavity, and these are the region of the sand, or this is the mold. and we are filling this cavity from here. Molten metal is coming here. This is sprue. So first what will happen, the molten metal will fall in this region here. So now even if it will, if even if will damage or erode some portion of mold in this region, it will not going to affect the cavity. So all the momentum transfer will happen here itself. So molten metal will fall here, and after that it will allowed to enter in the cavity from the bottom of the cavity. So it will, the cavity will fall from top bottom to the top slowly. So this is the another arrangement. It is called bottom gating. So earlier one was the example of vertical gating. This one is the bottom gating. So here what advantage we will get? Advantage is that there is no chance of damage to the cavity, but challenge is that the molten metal have to travel a longer distance. So earlier it was directly coming into the mold. Now it is falling here, and then it is entering in the mold after traveling certain distance. So its metal, molten metal should be poured at the higher temperature, so that during traveling, even if it loses the heat, then also it should remain in liquid form. So it should not get solidified in between. So that is the challenge. And inclined gating, no, this is not a type of gating. So vertical gating, bottom gating, these two are the possibilities. And which of the following type of gating mold is filled from bottom to the top? So that is the bottom gating. So we have seen the advantages as well as disadvantages of both type of gating system. So it is clear to everyone. If you have, if any of you have doubt, please let me know. Otherwise, we will move to the next problem. Okay, it seems there is no doubt. So we'll move to the next problem. Please read the question and first try to solve it by yourself. After that, we will together solve it. If you have any doubt, you can ask me regarding the question. For simplicity, you can consider it as a top gating system. That will simplify your problem. So considering that, please solve it by yourself first, then we will together solve it. Till now, I haven't received any response. So, whether it is clear, the question is clear to everyone, or some confusion is there. Okay, let me help you by drawing the diagram. Probably that will help you out to uh, to get the answer quickly. Okay, it has been given. The height of the down sprue is 100 mm, and its cross sectional area at the base is 300 mm square. The cross sectional area of the horizontal line is 300 mm square. Assume no losses. Calculate the time in seconds. Uh, we have to calculate the time for the cavity filling, and its volume is this much. And for simplicity, we can take gravity. The value of acceleration due to gravity is 10 meter per second square. So, uh, okay, first I will draw the diagram. Then it might be easier for you. Yes, Weber has got the answer. Yes, correct. So, suppose we have cavity something like this. So something like this. Now we are filling the molten metal from here. So what is given? The height of the sprue is 100 mm. So this height, this is 100 mm, and the cross sectional area at the base is 300 mm square. So this area, talk about this area, this is 300 mm square, and the cross sectional area of horizontal runner. So this is the runner. So it has uniform cross section, and it has also area same as this bottom of the sprue, that is 300 mm square. So this area is also 300 mm square, and the volume of this cavity is to 10 to the power 5 mm cube. So now molten metal is uh, filling inside this cavity. So what we have to find out, that is how much time it will take to fill the cavity. So since here the cross section area of the runner is same as the bottom of the cross section area of the sprue, so whatever the flow rate will be here, that will be same throughout the runner. So in this region, the flow velocity will be same as the flow velocity in at the bottom of the sprue. And if you remember, then what is the velocity? So if we try to find out the velocity of the molten metal here, then that will be given by velocity or root 2 gh. Okay, and the same velocity will remain throughout the runner to this point also. the velocity will be same as the velocity at this point. So if we want to calculate the time of filling, then what we have to do, we have to multiply the flow velocity with the area of the cross section of the this channel or runner, and we can calculate the time by using the volume. So if we multiply this velocity by area of the runner or the gate, that will give the volume flow rate of the molten metal. So now we know the volume flow rate of the molten metal, and if we want to calculate the overall time, then what we have to do, we have to divide the volume flow rate by total volume of the cavity. Okay, now it's easy. So what we'll do, we will substitute the values. So it will come, so volume is 3 into 10 to the power 5 mm square, and this velocity is, that is under root of 2gh 2 into g. Since all dimensions we are taking in the mm, so we have to convert this g, which is given g is equal to 10 meter per second, 10 meter per second square. If we convert it into the mm per second square, then it will become 10 into 1000 times of mm per second square. So if we write the value of g in mm per second square, then it will come this much. Okay, and now we have to multiply it by height of the mold, that is 100. So this is the volume, this is the volume, this is the flow velocity or small v, and now what is left, area of the gate, that is directly given 300 mm square. Okay, now if we solve it, then we will get time directly in seconds, that will come 0.71 seconds. So uh, this is the time for the mold filling. So I have explained the answer, so correct answer will be the B. So is it clear to everyone, or still there is some doubt? Okay, it seems there is no doubt. Okay, so we can move to the next question. Even if you have any doubt, you can ask me later also. Please read the question and try to give the correct answer for this. You can write your answer in the chat box. Till now I have got from the Vaibhav. I am waiting for others. Okay, so let's try to see it together. So which of the following is not true with respect to the aspiration effect? So if you can recall what was the aspiration effect, so let me tell you briefly. Suppose we have a cavity. Okay, so this is the cavity we have, and this is the sprue, and we are filling this cavity by molten metal. So we have molten metal here, and the molten metal is coming down in order to fill the cavity. Okay, so aspiration effect is it is basically, if during this whole process, during the filling of the cavity, if some gases which is present inside the cavity or inside the mold, so if you see from outside, this is complete mold. Okay, this is sand. Okay, how this mold is made? Mold is made up of sand plus water plus clay plus some additives. Okay, so in the mold material, or this sand are binded by with the clay, as well as some additives are also present inside this mold material. So aspiration is nothing if the gases which are not currently, earlier they were not present in the molten metal, but somehow during the mold filling process, if they enter into the molten metal, so that is called the aspiration of gases. So let's try to see all the options one by one, and I will explain why it is happening. So first option is, it is produced when there is sudden change in flow direction. And second is, it is produced when pressure falls below atmospheric pressure. So so when any gas can enter inside the molten metal, so that can be only possible when, if we create some vacuum, or we can create some pressure which is lower than the atmospheric pressure, then only it is possible to enter the gases which are which were not earlier present inside the molten metal, then they will enter into the molten metal. So now let's zoom this part. So what is there? So now I have made a vertical channel or vertical sprue. So if molten metal will fall from top, so it will, just if you see the shape of the flow of molten metal, it will be something like this. So why this shape happens? You can remember your fluid mechanics. So here the velocity is smaller, velocity of the molten metal is smaller. So let's say small v, but when it reaches there from height h, then its velocity get increases to, let's say, v plus some alpha, or directly we can write this as capital V. So one thing is clear: when we molten metal falls from the top of the sprue to the bottom of the sprue, its velocity increases. Okay, and again, if you use your continuity equation, so if you calculate the cross section area of the flow here and cross section of flow here, you will find, you can write something like this: a at the area at the top into velocity v is equals to velocity at the bottom and area at the bottom. Now this equation will always hold. Now this equation will always hold, and since this is greater than this is this velocity at the top, therefore the area of flow at the bottom will decrease, and because of this decrease in area, there is a gap. Okay, there is gap, and at the top of the sprue the pressure was atmospheric pressure, and if you again solve the Bernoulli's equation here and there, or from top and bottom, then what you will find? You will find the pressure in this region is less than P atm, because here the flow velocity has changed, and because of that, this is the reason where the pressure goes below the atmospheric pressure, or we can say it is vacuum. Then what will happen? So there are gases present inside the pores of the walls of the mold, nitrogen, hydrogen. So all these gases are already present in the mold walls. When they find negative pressure, then what they will do? They will come out from the mold walls or the pores of the mold, and they start diffusing into the molten metal. So in this way, they enter inside the molten metal. So it has happened only because we created a small vacuum region near at the bottom of the sprue. So the second option, it is produced when pressure falls below atmospheric pressure. Yes, it is correct. So air which are present inside the mold walls, they enter into the molten metal because the pressure went down from the atmospheric pressure. Again, this kind of phenomena takes place if we provide sudden bend or sudden turn. If we provide, like, suppose we have a sprue like this, just after that we provide a sharp change here. So molten metal is coming down here, and if we provide sudden turn, then what will happen? Our just after the second sudden turn, there is process. This type of vacuum or the shape of the flow will become something like this. So there is just some depression you can see in the flow, and this is the reason of the vacuum, and this process is, or this is called the when a contractor, so this has took place only because we give a sudden turn to the moving molten metal, and because of this again here we created vacuum. So the first option, if we see, it is produced when there is a sudden change in flow direction. So again, by changing the direction, we are creating a vacuum region. Then also the whatever the gases present inside the mold walls here and here, again they will enter into the molten metal. So again, this is called aspiration effect. So first and second are correct, and third one is it is produced when gases enter into the molten stream. Yes, it is the how it is the definition of the aspiration effect, third one. So if we see, first, second, third all are correct. So correct answer is D1. All the statements are true. So any confusion? Okay. If there is no confusion, then let's move to the next problem. Please read it, and you can give your answer in the chat box. Okay. Yes, I have got the answer from the Vaibhav and Nagasri Nivas also. So yeah, both of you have got the correct. So okay, let's quickly discuss it together. So which of the following is not the correct match of getting components and their function? Okay, so first one is pouring basin, splash coat, strainer, skim valve. So again, we can take the example of the diagram which has been discussed in the course lecture also. So I will take similar example. So this is our cavity. And so this is the pouring basin, and this is the cavity or mold cavity where we have to fill the molten metal. So this type of shape is provided in order to reduce the erosion, because normally what happens, we have furnace somewhere uh, somewhere away from this mold. So either they get here we get the molten metal. So the molten metal get transferred from either by the ladle or directly there is some channel through which the molten metal comes to the mold. So already molten metal have some momentum and velocity. So it is a pouring basin. It is a kind of a reservoir where initially the all molten metals comes and they get filled here, and after that gently the molten metals falls from pouring basin to the sprue. So the pouring basin has job of reduce the erosion of the molten metal which is coming from the furnace or from the ladle. So what happens after that? In the sprue, the whatever the molten metal comes, it has um, some impurities. If it is just some flux or some dross or some solid impurities, basically what they are, uh, they needs to be filtered. Otherwise, our casting have unwanted contaminations. So we want to remove any kind of solid impurity if it is has. For that, what we provide ceramic strainers. So this is the ceramic strainer. Since ceramic has very high melting point, that's why don't get uh, they don't get melted, as well as uh, we have you have also heard the word like foams or filtering foams. So those are made up of ceramic, and their job is to filter out any kind of solid impurity if it is there inside the molten metal. Okay, so whatever the molten metal will pass through the ceramic, it will be free from any kind of solid contamination. Again, what will happen? The molten metal will pass through the ceramic filter and it will fall at the bottom of the sprue. But at the bottom of the sprue, in order to avoid any erosion or splashing, again there is we there is a ceramic splash core is given. So it is splash core. It is also made up of ceramic. So its job is to avoid any kind of erosion at the bottom of the sprue or splashing. So if we avoid any kind of erosion, then it means we are not allowing any kind of solid impurity to get added from inside the molten metal. Suppose if some erosion would have taken place, then again our molten metal would have become contaminated. Since we provided the splash core, so that will not happen. So splash core is here. Again, after that, the molten metal pass through the runner and it enters into the cavity. So a last filtering option is provided, that is called the skim bob. So it's it is a kind of bulging area which is provided at the top as well as the bottom. So still, if there is any minute solid contamination is there, if it is heavier, then it is get collected at the bottom portion. Heavy impurity, heavy impurity. But if some lighter impurities are there, they are floating at the top of the molten metal, then they will get trapped here. So this is a lighter impurity. So this is the overall function of all these components. So let's try to look at them. Option A, pouring basin increases the eroding force. No, it's wrong. It decreases the eroding force. And splash coat reduces the eroding force. Yes, it is correct. Strainer, it removes the dross or solid waste. Correct. Skimbob prevents heavier and lighter impurities from entering into the mold. It is also correct. So correct option for this question is the first one. So it is not correct. So is it clear? If you have any doubt, please ask me. Okay, since there is no doubt, so we will move to the next problem. Please read the problem and you can give your answer in the chat box. Yes, Vaibhav, you are correct. Yes, yes, both of you have got the correct answer. So I will quickly discuss it. So, sprue design is made tapered instead of straight. Yes, it is similar thing which we have discussed just a few minutes ago. So again, I will draw the schematic. Suppose we have a cavity like this, and I have told that when molten metal will starts from falling from here to top to the bottom, then its cross section of flow gets reduced, and because of this, there is a possibility of formation of vacuum region, or pressure goes down below the atmospheric pressure. So in order to avoid any kind of aspiration effect, so what it is common methodology is to, rather than making the sprue of uniform cross section, it will be better if we could make it some tapered. So if sprue will be like something like this, then we can avoid the any kind of aspiration, because now there is no gap between the molten metal and the walls of the sprue. So now sprue is completely filled, so no formation of vacuum and no aspiration effect will take place. So here possibility of formation of vacuum, that will lead to the aspiration of gases. Aspiration of gases. Here no vacuum formation, no aspiration, and therefore no contamination of molten metal. So correct answer is to maintain the pressure balance. So already you have got the correct answer. So we will move to the next problem. Please read the question and you can give your answer in the chat box. After that, we will discuss it together. Okay, Vaibhav have given his response. I'm waiting for Naga. Okay. Okay, let's try to discuss it together. So, what has been asked in the question? What among the following can be most appropriate reason for the velocity of fluid in contact with any solid surface to be zero? Okay, so we'll take a simple example. Uh, suppose we have uh, any any fluid which is running inside a pipe. So suppose this is the pipe, or for most relevant, we want, let's assume it is runner, or let's say pipe. So both are similar conditions. So inside runner, what happens? Molten metal, it comes. So molten metal comes and it flows through the runner. Okay, it's cavity. So if we if we see the if we see the velocity profile of the flow, then it will come something like this. Wait, I will change the color. Okay, so if we see this in the center region, the velocity of the material is flowing at higher velocity, whereas the near the walls, here the velocity of the metal is zero. Here zero velocity. Here also it's zero velocity. So why it is happening? Why here the velocity is zero? So you have come across two words like adhesive force and cohesive force. And cohesive force. So cohesive force, it is the force between the same kind of molecule, or it is a force between the molecules of same material. Molecules of same material. Whereas the adhesive force, it is the force between molecules of different materials, or I should write here force between molecules of dissimilar material. Okay, so if we see, if we zoom out this, what we find here, we find that this is the wall, this is the wall, and this is the wall of the mold, and here this is the molten metal. This is molten metal, and this is mold wall. Mold wall is made up of sand, binder, water molecule and clay, whereas the molten metal is it is a metal, pure metal, or it is alloy. So here if we see this interface, in this interface the contact is between dissimilar material. So if the bond between this mold wall and the fluid which is very close to the mold wall, it is very strong, then the molten metal, the molecules of the molten metal which they get bonded to the walls of the mold, and therefore they will not move at all. So the force which will act between these two, it is adhesive force. Okay, so again I will zooming it out. So these are the molecules of molten metal, and these are the molecules of mold wall. Okay, now if so, here we have adhesive force, and there is a force between the molecules of the metal itself, like between these molecules. So this is the cohesive force. If the adhesive force is higher than the cohesive force, then what will happen? Then these molecules, they are flowing, they will not able to drag the molecules which are already bonded with the mold walls. So if adhesive force is greater than cohesive force, then the molecule which are very close to the mold wall, they will stick to the mold wall and they will not move, whereas the molecules of the molten metal, they will keep on moving. So this this zero velocity condition, this is called no slip condition. Okay, and this no slip condition occurs because of strong adhesive forces. Okay, so now let's start looking at the options. First one is no slip condition. Yes, that is correct. Cohesive forces in the fluid particles. No. If cohesive forces in the fluid particles were strong, then they then the molten metal would not have been stick to the mold walls. So it is wrong. Low velocity of the fluid. No, this is not correct, because there it is zero velocity, because there is a strong bonding between the molecules of the molten metal and the mold wall. And high intermolecular forces between the fluid particle, it is same as the cohesive force, so it is same as the B option, so it is also not correct. So the only no slip condition or the adhesive force is responsible for the zero velocity of the fluid near the walls. So correct answer is A. So is it clear? Or if any of you have any doubt, please ask me. Okay. Okay, it is clear to everyone. So let's move to the next problem. Please read the problem and you can type your answer in the chat box. Okay, Nagasil Nivas has given his response, and I'm waiting for others. Okay, Vaibhav also has given his response, so let's discuss it together. Okay, so which of the following gating system is used to avoid the splashing of molten metal in the mold? So already we have learned vertical gating, bottom gating. I will again tell about the parting line gating, and there is no type of inclined gating, so it is not correct anyway. So we have studied these two. So similar to that, we will learn uh, the parting line gating. So in vertical gating, we have learned we have mold something like this, and this mold is getting filled directly from the top. So molten metal is coming here. This is the vertical gating. And in the bottom gating, we have learned so molten metal is coming from top to the bottom. Sorry, from bottom. So mold is getting filled from the bottom. And similarly, if we have if our cavity is something like this, and it is getting filled not neither from the top neither from the bottom, so somewhere it has parting line. So this is drag, this is scope, it is parting line. So here molten metal is coming from here, and it is getting filled from the parting line. So I have told that in the vertical gating system we have advantage of quicker filling, but we have a risk of erosion or splashing because material is falling from this much height. Molten metal is falling from this height, so the molten metal have momentum, and if the mold strength is not good, then the problem of erosion or splashing, metal will fall and it will get splashed and erosion may take place. So in order to avoid this, uh, one option is go for the bottom gating. We can avoid the erosion because material will fall first here at the bottom of the sprue, and when gently it will enter inside the mold, so it will not damage the mold at all. But here the molten metal has to travel for longer distance and for longer time, so here the temperature of molten metal should be higher. Sorry. So here uh, chances of solidification of molten metal is high. Is possible if molten metal is not sufficient hot, then it will start solidifying in between. So that is the disadvantage of bottom. So what people have tried means they found a middle way. So they then they took the advantage of both vertical gating as well as the bottom gating. So here, if we fill the molten metal from the parting line, then molten metal will fall from only this much height. So the problem of erosion and splashing get reduced. Splashing and erosion, it will get reduced. And in compared to the bottom pouring, here metal will reach in shorter distance and in shorter time. So there are less chances of solidification. So this is the parting line gating. So which of the, if we see the question, which of the following gating system is used to avoid the splashing of the molten metal in the mold? So the most appropriate answer will be the bottom gating, because here we are not saying anything about this solidification. So if we just focus on the problem of splashing, then the bottom uh, then the bottom gating is best, and after that parting line gating will come, and vertical gating is poor. So most appropriate answer will be the D1, and already you have given the correct answer. So there is uh, so it must be clear to all of you. So let's move to the next problem. Please read the question, and you can give your response in the chat box. Okay. Okay, I have got response from two of you. Okay, so let's quickly discuss this question. Solidification plays an important role in deciding which of the following characteristics of the casting. So if we uh, let's make a mold. Okay, now what will happen? This mold will filled with the molten metal. Okay, so when this cavity is filled with the molten metal, then what will happen? Since this molten metal is at higher temperature, so what will it do? It will start transferring heat. So heat transfer will be higher in which region? So it will be near the mold walls, because mold walls are in the contact of the molten metal directly. So by the conduction mode of heat transfer, the molten metal will quickly start transferring heat to the mold wall, and therefore its Therefore, the temperature of the molten metal will fall quickly near the mold walls, and near the mold wall, solidification will start first. So, in because heat transfer happens very faster near the mold walls, therefore solidification will start first from the near the mold walls. Okay, so there is another thing like solubility of the different components of the molten metal. So suppose molten metal, it is made up of some alloy. So suppose if we are talking about uh, steel, then we have iron, carbon, and when molybdenum, nickel, cobalt. So there are different elements are there, and each of them have uh, different solubility, uh, different solubility at different temperatures, and therefore the concentration of the alloying element, it it keeps on changing. So suppose this is our mold wall, okay, and just after pouring the molten metal, the metal near the mold wall gets solidified. What will happen? This is the interface of molten metal and solidified metal. Okay, so what will happen? Then since there is a difference of the concentration of the alloying element inside the molten metal. This is the molten metal region. Here the nearby the interface region, this is the high concentration region. In this region, alloying components will become higher, or the concentration of alloying element. And in order to understand why it is happening, you can refer to the lecture of the week 3. There, sir has explained it nicely, means why the, the, the regions nearby the solid liquid interface, there is a higher concentration of the alloying element in the molten material. So uh, that will happens, and because of this, because of difference in the concentration of alloying element, we get a compositional variance, or there is a gradient of composition from if we after the complete solidification. Suppose after complete metal gets solidified like here, and if we check the composition near the walls, mold walls, and if we check composition in the core of the casting, we will find a difference, because core region will solidify in the last, and therefore alloying element percentage will be higher percentage of alloying elements. So here near the mold wall we will get less concentration of alloying element, in the core we will get higher. So we will find a gradient, of various components throughout the casting. Also, because the composition is changing from wall to the core, so alloy composition will also change at the different location of the casting. And because of this, because of this there are uh, different possibilities of the grain growth or crystal growth. So there might be chances, if we cannot control the solidification process, then there is a possibility of formation of different types of grain. So out of one is called the dendritic grains. So solidification is takes, suppose this is the direction of solidification, but suppose some condition happens so that the here in this region composition change has taken place in such a way that it's the region, the material in this region feels becomes subcooled, it becomes subcooled. So because of change in composition, its solidification temperature will also change. It will, if it will become lesser in these regions, then these materials also starts gets solidifying, and because of this we get this kind of dendritic grain structure or dendritic crystal structure. So but this is not desirable, because of this we get different kind of defects like porosity, microvoids. So those things are not desirable. So we try to avoid the dendritic structure. We always try to get, sorry, we always try to get equiax grains or non dendritic structure. So the basically what I wanted to say, uh, if we control the solidification rate or the solidification process, then we can control the grain structure of the casting as well as the compositional gradient, or the difference between the composition at different locations of the casting. That thing we can control. So solidification is very important phenomena. If we can control it, then we can uh, control the properties of casting. So one of the example is like we can use chills. We can use chills so that where we can get the required directional solidification. So that is the one of the possibility. So if we see the correct answer of this problem, that will be the all the above, because all this phenomena totally depends on the solidification process. So the correct answer is D. So any of you have any doubt? Okay, it seems there is no doubt. Then let's quickly move to the last question of the day. Please read the problem and you can give your response in the chat. Okay, yes, correct. All of you have got the correct answer. So again, we'll quickly discuss for everyone. So the direction of crystal growth in an alloy is most dependent on which of the following factor. So again, I will take the same example. We have this mold, and this mold is filled up with molten metal. Okay, this is the sand. Okay, and as already we have discussed, uh, when solidification process will start, begins from the begins from the near the walls of the mold, and near what will happen, the grains will nucleate near the walls of the mold, and it will keep on growing towards the center. So why it is happening? It happens because of the temperature gradient. Because here, the because of conduction, the heat has transferred by conduction, and the temperature near the mold wall, it felt down quickly, and therefore solidification started from the mold wall. And similar manner, it's start moving towards the center. From each side it will happen. So indirectly, if I want to say, if we can control the thermal gradient, then we can control the direction of the solidification or the direction of the crystal growth. So the correct answer will be the B, thermal gradient within the mold. Whereas other factor, atmospheric pressure, even if we change the pressure, then we cannot change much the direction of the solidification. So it is not a correct answer. Atmospheric temperature and pressure, because they are not coming in the contact of the molten material, so it won't affect anymore. Only thing is molten material coming in the contact of the mold walls, and from there, if we can control the temperature gradient, then we can control the direction of the crystal growth. So correct answer is B. So already all of you have got the correct answer. So still, if any of you have doubt, please let me know. Otherwise, we can end this session here, and we will meet next Tuesday at the same time. So is it clear to everyone? Okay, thank you, Srinivas. Okay, if you have any doubt, please ask me. Weber, you have doubt? Okay, it seems there is no doubt. So we will end the session here. Okay, good night. Good night, everyone, and we will meet next Tuesday. Thank you.